Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 14, seminar 5, in which we will solve our next problem, number 15. In the previous several seminars, we solved some number of problems that dealt with circles that touch. But starting from this seminar, we will solve several problems that deal with circles that are orthogonal. To that end, in the current problem, the problem number 15, we're asked to construct a circle that satisfies the following two constraints. That solution circle should be orthogonal to a given circle, and it should also pass through two given fixed, distinct coplanar points P1 and P2. When we begin analyzing the material that is given to us in the problem number 15, we quickly realize that the mutual juxtaposition of the objects that are given in this problem has some number of variations. In other words, with respect to the given circle Q, named lowercase q and shown in blue on the right side of your screen, that has the center of the point uppercase Q, and the two given points P1 and P2 that are both fixed, distinct, and coplanar with the plane in which the given circle is located, we have the following variations. Both of these points can be located strictly inside of the circle Q. Both of these points can be located strictly outside of the circle Q. Both of these points can be located somewhere precisely on the circle Q, and the points can also stagger the given circle. For example, the point P1 can be located strictly outside of the given circle, while the point P2 is located inside, and conversely, the point P1 can be inside of the circle Q and the point P2 can be outside of the circle Q. Evidently, because of the placement of this problem within this specific course, it is evident that we're looking for situations which admit, or we're looking for the mutual juxtaposition of the given objects that admit an interesting number of solutions, each of which can be algorithmicized using the machinery of inversive geometry precisely. And for that particular reason, we will consider the case, for demonstration purposes, I will consider the case when the point P1 is located, let's say, strictly outside of the given circle, and the point P2 will be located somewhere strictly inside of the given circle Q. And also, on top of all these mutual juxtapositions of the points with respect to the given circle, we can also sprinkle the situation when the given points P1 and P2 are collinear with the circle Q. But like I said, we will consider this case at the end of this episode. For now, we will only look at the juxtaposition of the points P1 and P2 such that these points are not collinear with the center of the given circle. To that end, one way in which the problems in which a number of or a multitude of like objects is given are solved is using the following idea. We temporarily eliminate from the consideration all the like objects but one. In this case, that means that temporarily we forget, for example, about the point P2. We only deal with the point P1. And in that respect, we pose the following question. Given the circle Q, how many circles that are orthogonal to that circle and pass through the point P1 can be constructed using the Euclidean tools alone, a compass and a straight edge, with absolute certainty and evidently correctly? Well, the answer to that question comes to us from the theorem number 39, the theorem that we proved in one of our last lectures, lecture number 8 or lecture number 9. And at this point, it is beneficial to recall the technical essence of the proof. How did we prove that theorem? Well, we said that if we reflect the point P1 in the given circle with positive power, the power is always positive, and we do this reflection exactly once, then we will obtain a line segment. Let's say the line segment delineated by the points P1 and P prime 1. Then we bisect that line segment with the perpendicular bisector B1 in such a way that the point at which the bisector and that line segment intersect cuts the line segment P prime 1 P in half. So we have this line segment by length is equal to this line segment, and the angle that the perpendicular bisector B1 forms with the line segment P1 P prime 1 is pi over 2 radians. Then what was the next step? We picked an arbitrary point, let's say this point right here, and we claimed that that point plays the role of the center of a circle that passes precisely through the points P1 and P prime 1, and we showed that in this case that circle is orthogonal to the circle, to the given circle Q. What was the gist of that proof? Well, in some sense we delegated all the heavy lifting of that proof to the theorem from the theory of circles, or a theorem that Euclid proves in his book Elements, book 3, proposition 37. Basically, the technical gist of that theorem claims that the rectangle on the second to a circle is equal to the square on a straight line that falls on that circle. And if that's the case, then the straight line that falls on that circle is tangent to that circle. And if it's tangent, then it forms the angle of pi over 2 radians precisely with the radius of the circle which is under consideration. And in our case, that meant that the two radii form the angle of 90 degrees, and that precisely means that the two circles are orthogonal. And if we move that point along the perpendicular bisector, then we obtain what? Well, in some sense, that perpendicular bisector can play the role of what? Of a real number line. There are uncountably infinitely many real numbers. Consequently, there are uncountably infinitely many circles that are orthogonal to the given circle, that pass through the given point, and each of such circles can be constructed evidently with Euclidean tools alone, a compass and a straight edge. When I was presenting the proof of the theorem number 39, I put together an animation for you to show that idea, but I did not make the main character of that animation the perpendicular bisector B1. I only emphasize the fact that the points P1 and P prime 1 are the inversive images of each other with positive power in the given circle. But in order to underscore the fact that for this problem, our perpendicular bisector B1 will be the star of this show, I've put together another animation for you where I exercise 2 degrees of freedom, not 1 degree of freedom as you saw for the in the animation of the theorem number 39, but 2 degrees of freedom. And what does that mean? That means that in the animation that you're about to see, I fixed the circle of inversion on the left side of the animation that you will see. That circle will remain in place at all times. Inside that circle, I picked a sample point that will orbit a small circle that I will not show in order to avoid the clutter. But the fact that that sample point will orbit a circle in the plane will already exercise 1 degree of freedom, so that sample point will move about in some way. Consequently, its inversive image will trace a certain circle that I also hid in order to avoid the clutter. So we'll have 2 inversive images of each other tracing a certain orbit, roaming, let's say, the parent plane. And then I constructed the perpendicular bisector B1 of such 2 points. And that perpendicular bisector will also dance around in the parent plane in a certain way. You will see that in a second. And what is the second degree of freedom in the animation that you're about to see? On that perpendicular bisector, I animated the point that will run up and down that bisector, and that point will play the role of the center of a circle that passes through 2 inversive images with respect to a certain circle, and that circle will always be what? orthogonal. That circle will always be orthogonal to the fixed circle of inversion that you will see on the left side of the animation. So in this upcoming animation, I recommend that you pay attention to the yellow dot where the two circles intersect, and to the dot I drew the radii from two circles, and you will see visually that the angle between the radii of these two circles always remains right. Once that idea is understood, we can completely solve the problem number 15 using the so-called method of intersecting loci, which circles back precisely to the idea that I mentioned a few seconds ago, where we eliminate all the like objects but one, solve the problem for that one object, one characteristic object, and then we bring in all the remaining objects. That is, we just showed that the locus of all the centers of uncountably infinitely many circles, each of which is orthogonal to the given blue circle Q, and that passes through the given point P1 is what? Is the perpendicular bisector B1 that is constructed on what? On the line segment that is delineated by the given point P1 and its inversive image P prime 1 with positive power with respect to the circle Q. That much is understood. Likewise, we now bring one by one all the like objects. How many such objects we have? Well, only one, the point P2. Consequently, the idea is exactly the same. The locus of the centers of uncountably infinitely many circles, each of which is orthogonal to the given blue circle Q and passes through the second given fixed distinct coplanar point P2 shown over here in yellow, for example, will be what? Will be the perpendicular bisector B2 constructed to the line segment that is delineated by the point P2 and its inversive image P prime 2 with respect to the given circle Q with positive power. Also, this reflection is carried out once. That task can also be completely accomplished using the Euclidean tools alone. We know how to do that. Now, there is an if statement hidden over here. So if the perpendicular bisectors B1, shown in green, and B2, shown in yellow, intersect, this is the method of intersecting loci in all its glory. They will intersect precisely over one unique point, O, let's say we call that point, and it will so happen that that point will be equidistant from all 4 points of interest, from the given point P1, from the given point P2, from the image P prime 1, and from the image point P prime 2. On my drawing, of course, it looks absolutely out of proportion, but I recommend that all of our viewers carry out this particular construction using their favorite graphing software, do it so-called professionally. And in the animation that you just saw, for the animation that you just saw, I used the free software called GeoGebra. Once you do all the steps with a graphing software, you will precisely see that this will be the case, and all these things will work out beautifully. And we can now put together an algorithm that solves the problem number 15 in general. To that end, in order to construct a circle that is orthogonal to a given circle and passes through two given fixed coplanar points, we execute the following basically 3 steps. First, we reflect the given points P1, 2 in the given circle Q with positive power once into their corresponding reflective images P prime 1, 2. That's step number 1. That reflection can be done with Euclidean tools alone with absolute certainty. We know how to do it. We carried out all the corresponding steps in the corresponding problems. We proved the respective theorems. This is all nice and clean. It can be done. Second, we bisect the line segments P1, P prime 1, and P2, P prime 2 with the perpendicular bisectors B1 and B2. This is the step number 2. Each of the steps can be carried out with Euclidean tools alone, with a straight edge and a compass. This is also can be done beautiful. And the third step, implicitly, or let's say quietly, there is an if statement over here, but again, in the most general case, we will assume that the perpendicular bisectors B1 and B2 will intersect over a distinct or unique point. O, let's say we will name this point O. That point is shown in red. Perpendicular bisector B1 shown in green. Perpendicular bisector B2 over here shown in yellow. In this case, of course, I artificially concocted the situation where these two perpendicular bisectors intersect over a unique point O, and in this case that point will be equidistant from all 4 points of interest. And as the final step, we draw a circle W. Let's say we call this circle lowercase w. This is our solution circle that has the point O obtained in this step as the center, and its radius is the distance from that point O to all 4 points of interest, P1, P2, P prime 1, P prime 2. And the claim here is that that circle W with these parameters will be orthogonal to the given circle Q, and it will pass through the given points P1 and P2. For a proof of that statement, I will leave the proof of that statement as an exercise to the viewer, but it should be understood that that proof is basically self-evident, and our analysis that we carried out in the previous segment pretty much is a proof, because here we will invoke the theorem number 39 for the point P1. We will invoke the theorem number 39 for the point P2 if it holds for the point P1, and if it holds for the point P2, it holds for both of these problems, for both of these points. Problem solved. And now the only one case that we will talk about very briefly. In general, I will leave the analysis of all the other cases to the viewer. For example, let's say we have our points located, the given 2 fixed coplanar points are located precisely on the circle Q. What will be the solution in this case? Well, this is trivial. We simply draw 2 tangents to the given circle through the given points, and where these tangents intersect, boom, this is the center of the circle that will be orthogonal to the given one and passing through the 2 given points. This is not interesting. This is baby middle school geometry, if you will. There is no to bring in the machinery of the inversive geometry of the real plane with respect to a circle. And what if these 2 points are diametrically opposite of each other? Well, that means that the points P1, P2, and the center of the given circle Q are collinear. And this brings us to the point for the implicit if statement over here. What if the bisectors B1 and B2, the perpendicular bisectors B1 and B2, do not intersect? Let's say B1 and B2 do not intersect. What does that mean? Well, that means that the perpendicular bisector B1 is parallel to the perpendicular bisector B2. The perpendicular bisector B2 is somehow parallel to the perpendicular bisector B1. And what does that mean? Well, that means that in this case, it can be only one situation where the points B1, B2, and the center of the circle Q are collinear. In other words, we have the show of points that are collinear. All these points somehow belong to one straight line. And here is the interesting situation. In general, the so-called classical Euclidean plane or the real plane. In such a plane, no two parallel straight lines ever intersect. But remember, in one of our first lectures, we equipped our real plane with the so-called point at infinity. And what is the point at infinity? The point at infinity is a geometric image of the north pole of the Riemann sphere under the stereographic projection of that sphere onto the underlying Euclidean plane. Equipped with the point at infinity, our Euclidean or real plane becomes the extended Euclidean plane or the extended real plane. And in that plane, it can be taken that the two parallel straight lines do intersect, but they do intersect at that point at infinity. And in this case, our circle, the solution circle W, look at this. What will happen to this solution circle? As our, let's say, yellow perpendicular bisector rotates in some funny way, bringing the point P2 in line with the straight line that runs through the center of the circle Q and the given point P1, what happens with the point O? The point O, look at this, it will run. It will run where? Exactly, it will run into the point at infinity. And what do we call a geometric object, or what do we call a circle that passes through a given, let's say, 3 points, P1, P prime 1, let's say, and P2, and has its center at the point at infinity? Well, that circle is called a straight line. And then evidently it should be also quite obvious that in this case, if we're given a circle, then the straight line that passes through the center of the circle, which it must necessarily do because all 3 points of interest are collinear, that straight line will be orthogonal to the given circle because the tangents constructed to the given circle through the points where the straight line meets that circle will be what? They must be orthogonal to that straight line. And all the remaining cases that may arise, you should analyze on your own, but keep in mind the fact that when the center of a circle is taken into the point at infinity, then that circle becomes a straight line, but that only happens in the extended Euclidean plane or in the extended real plane, the plane that is equipped with the point at infinity. Now, this is it for the seminar number 5, and this is it for the problem number 15. And as a fair heads up, in the next seminar, in the problem number 16, instead of dealing with one circle and 2 points, we will be dealing with 2 circles and 1 point. As such, you may want to start thinking about how will you construct a circle or maybe several circles that are orthogonal to 2 given circles and pass through a given point.